So in this example, we have a region between two curves here. We have g of x is above the f at x, and we're going to rotate this region about a different horizontal line. We're not going to revolve around the x-axis as we did in part 1 video. We're going to rotate this about the horizontal axis y equals -3. So it's a similar volume formula. We're still going to have the pi here, um, but and we're going from, in this example, -1 to 1. Um, so g of x is above f at x. So the radius, when you spin it around the y equals -3, the radius is not just going to be the g of x, it's going to have an additional 3 units because this line is 3 units below the x-axis. So it'll be g of x plus an additional 3 units. So this will be the radius, and you have to square that. And then we're going to subtract the f at x, again, the same reason in here. F at x, the radius, or the distance between f at x and the horizontal line y equals -3, will be f at x plus an additional 3 units. And we'll square that, d of x. Okay, so here is your volume formula here. Let me just substitute what g of x is and what f of x is here. Up here, we get pi, -1 to 1. G of x is 4 minus x squared, and we have to add an additional 3 units to that, and then we need to square that, and then subtract f at x is x squared plus 2, then add another 3 units to that. Don't forget to square that, and we get d of x. Let's do just a little bit more simplifying here. In the brackets here, we have 4 plus 3 is 7 minus x squared. Got to square all that. And then we subtract 2 plus 3 here. So it'll be x squared plus 5, all squared. Okay. So if we were to do this without a calculator, you would have to expand this, and you'd have to expand this as well, and then subtract. So there is expanding and simplifying here before you do any antiderivatives. I'm going to leave this as an exercise for you. I'm going to tell you what the answer is, so you may want to pause the video. If you don't have access to a graphing calculator, you have no choice. You have to expand and simplify and then antiderivatives. So if you want to go about doing that, do it now. I'll tell you what the answer should be. Okay, so using a graphing calculator, I got a final answer of 100.53096. In this example, we have a region here bounded above by a horizontal line y equals 12 and below by an upside down parabola 9 minus x squared. Let's call the parabola f at x and the horizontal line g of x. Now we're going to spin this around the horizontal line y equals 15. Now this is the first example where the rotational axis is actually above both curves. So you have a diagram here. So the rotational axis is up here at y equals 15. Now the larger radius is going to be formed from f at x to this horizontal line. Because that's going to be the larger radius, right? So for example, from say here, the distance from here to the horizontal line, what will that be? Well, this will be f at x, point B is f at x, and up here is y equals 15. So the difference between 15 and the f at x is this actual radius here, rotation. So that will be 15 minus f at x. So that would be the radius. So we have to square that. Let me set up the integral here. we're going from 0 to 3. So 0 to 3, and I'll put the pi out here. So that is the larger radius. The smaller radius is the distance from this horizontal line y equals 12 and y equals 15. And that's only 3 units. So we're going to subtract 3 squared. Actually, let me just erase this part here. Let me be consistent here. Let's use g of x. So as I mentioned, g of x is this horizontal line y equals 12. So the difference between 15 and g of x is that smaller radius, and we have to square that, d of x. Now 15 minus 12, because g of x is 12, that gives us the 3. Okay, so let me do that in the next step. So this becomes 3, 15 minus f at x. 15 minus f at x. Now f at x is 9 minus x squared, so I'm going to put that in brackets, 9 minus x squared. And of course the reason why I'm doing that is because 15 minus that, this minus is going to, when you're expanding this and simplifying, it's going to affect both the 9 and the negative x squared. So I emphasize that by putting brackets around that. And then we're going to subtract 15 minus g of x. G of x is just 12. And don't forget to square that. So I'm going to stop here. Okay, everything after this is just expanding, simplifying, and then the antiderivatives. You're going to be using power rules, the anti-derivative rules of power rules, and you're going to be substituting, and then right at the end you'll multiply everything by pi. So I'm going to use a graphing calculator to calculate this. If you have one, use it. This is an excellent example where you would actually pull out the calculator and let the calculator do all the work. But if you want to do it by hand, it can be done by hand. And if you want to do that, I'm gonna pause it. You should pause the video and go to work on that. I'll tell you what the final answer is. Actually, before I give you the final answer, let me just do the first step of simplifying here. Okay, so within this bracket here, you'd have 15 minus 9, and that'll be 6. And then when you subtract negative x squared, you get plus x squared. And I've seen students make the mistake of writing minus x squared many times. That's why I wanted to show you this first step. And then we have 15 minus 12, and that's the 3 squared dx. Okay, so final answer, my calculator reads 746.44241. Hopefully you got that result as well. In this example, we're going to revolve the parabola y equals x squared about the y-axis, the vertical axis here. So if we were to take a portion of this parabola, say from 0 to 2, so here, 0 to 2, so up here. So if we were to take this portion of the parabola and spin it around the y-axis, what would it look like? Well, let me try give this an attempt here. It would be this solid here, 3D parabola. So how would it go about calculating the volume of this? So we'd use the formula we know. It's pi times the integral. Now we're not going to put the boundary 0 to 2 because these are x values. We need to look at the y value. So the y value here is 0 and the y value here is 4. So 0 to 4. The lower bound is 0, upper bound is 4. And so that takes care of the limits of integration here. Now, what's the radius going to be? That's going to be the distance from the curve to the y-axis. Okay, so we have to rewrite the parabola, which is a function of x, right? F at x is equal to x squared. We need to rewrite that as a function of y. So the y value is going to be just the square root. So the inverse of a square number is square root. So the function here is f at y is equal to square root of y. So this distance here will be the square root of y. So we'll put that in there. And that's the radius, and we need to square that. And delta y this time. Okay, so that's what it would look like revolving around the y-axis. We need to change our function here to a function of y, and we need to change the limits of integration here. These are y values. So I'll work this one out. It's not so bad. It's not that messy here, because when you square the square root of y and you square that, you just get y. So the antiderivative of y is just 1/2 y squared, and we're evaluating that from 0 to 4. So that's pi multiplied by 1/2 of 4 squared minus 1/2 of 0 squared. And 4 squared is 16, divided by 2 is 8. So this is 8 minus 0, and multiplying by pi, we get 8 pi. In this example here, we have a region. The parabola here is y equals 9 minus x squared, and it goes from 0 to 3 in the x values. Here, we want to spin this region here about a vertical axis here. Not the y-axis, but the axis to the left, 2 units to the left, which has equation x equals -2. Okay, so we're going to spin this region around. There's space in between this left bound x equals 0 and the rotational axis. So that means when we rotate it around, we're going to get this solid with a hole in it. So this is one of those examples where it's a difference of volumes. So the larger radius is going to be from the curve, the parabola, to this vertical line here, x equals -2. So the first thing we need to do is isolate x here, because we need to write it as a function of y. So if we were to isolate, say, x squared here, we'd have 9 minus y. And one more step here, take the square root. So our f at y will look like this. It'll be the square root of 9 minus y. Okay, so let's set up our volume formula here. Pi, the limits of integration here, the y values go from 0 to 9. The distance from f at y to this x equals -2 will be this square root of 9 minus 3, but you'll have an extra 2 units here, an extra 2 units from here, the y-axis to there. So that'll be, we need to add that, so we have to add that there. Don't forget the square. And then we subtract the distance from the y-axis to the vertical line, x equals -2, is just 2 units. So we need to subtract that, and this will be all d at y. Okay, so that's the setup. At this point, it's all simplifying, expand, simplifying, calculating antiderivatives, and substitution here. So I'm going to leave this as an exercise for you, and I'm going to get out my graphing calculator, and I'm going to work it out, and I'll tell you what the answer is. So working this out, I get approximately 353.4. If you're doing it by hand, you have to expand this, and it takes quite a lot of work here. Using a graphing calculator saves you some time, and hopefully you got that result as well.